Today is National Science Day. February 28th was the day in 1928 when C.V. Raman announced a major discovery he had made in his laboratory with his students in Kolkata pertaining to light. So this talk is about light, and the title I have chosen is Journey into Light, which is the title of a book by G. Venkatraman, himself a well-known distinguished physicist, which describes the life and work of C.V. Raman. Now, I'm not going to describe what Raman did, but I would like to go back to the basic facts we learn about light and try and tell you something more about them. The very first thing we learn is that light travels in a straight line. We've drawn 2 points A and B, and sure enough, we have a straight line connecting them, and light travels along it. In fact, people who need a straight line often use a laser beam for that purpose in the construction industry and so on. But does it really travel in a straight line? Always. After all, you throw a stone, that doesn't travel in a straight line. It travels in a curved path, and we know that's because of the force of gravity. So the question which Newton asked himself, he guessed that light must be bent into a curved path by gravity, but he could not prove it with his mathematics, and it could not be seen by experiments. By the time of Einstein, early in the 20th century, he predicted on the basis of his mathematical calculations, his theoretical ideas, that this should really happen. And he asked astronomers to check this. And they came up with this very interesting experiment. What you're seeing here is the sun. And this is light from a distant star. Oh, it's really much further away than you're seeing in this picture. Passes near the sun. And if there was no force of gravity, the light would have ended up somewhere here on the tip of this arrow. But because of the effect of gravity on light, it ends up here. And this is just showing you a cartoon version of the Earth as a kind of blue planet. How much does light get deflected? I could tell you the angle, but maybe another way of expressing it is that it's almost 1,200 kilometers. So it's quite a large effect. And this would become larger and larger as light travels a greater and greater distance. And maybe 80 years after this experiment, we now have beautiful evidence, again from astronomy, that this happens on the scale of the whole universe. So this picture shows you at the center a galaxy, right? A faint collection of stars, faint because it's so far away. And you see these 4 bright objects. So you would think they are nearer, but actually they are much further away. Astronomers do have a way of measuring distance. And also, they are not really 4 objects, they're just one object, because all the measured properties of these 4 objects are the same. So what has happened is that there's one object lying behind this, and the light rays have been bent to reach you along 4 different paths. So something like a lens, okay? So this is called a gravitational lens, telling you that light doesn't always travel perfectly in straight lines. Now let's talk about reflection. We all stand in front of mirrors to see, how we look. But actually, what we see is not what other people see. All of you know that if you raise your right hand, the person in the mirror raises his or her left hand. And this applies to dress. If you happen to wear a sari on, say, your left shoulder, then you will turn out to be a Gujarati wearing out on the right shoulder in the mirror. So, can you make a mirror which shows you how you look to the rest of the world? And the answer is yes. You need 2 mirrors at right angles to each other. So let me show you what happens to light which comes, hits the first mirror, bounces off, and all of you know that these two angles are equal. The angle between light and the mirror with which it comes in and with which it goes out. And the same holds at the second reflection. Okay? So the net result is that light comes back in exactly the same direction as it went in. And those of you who play a game called Carom will know that this is the way you make this striker come back. You send it into a corner, hits these two walls and comes back. Okay. So that means that wherever you stand, the light will come back to you. Now I've drawn this figure in a plane. So long as you're at the same level as the mirror, this will happen. But what happens if you're above the mirror or below the mirror? Well, then you need three mirrors. Okay. So here is a picture of an object called a corner reflector. So these are not very good mirrors, but there are three of them meeting each other like corners, like the three walls at the corner of the room. And this is actually quite a useful device. This is placed on the edge of highways, many of them in a line, so that a motorist traveling at night will know where the edge of the highway is. Now, you could have placed lights, but then you would have needed batteries, you would have needed power to keep those lights going. Whereas this works beautifully. If there's no motorist, well, it just sits there. And the moment the car comes along, the light from the headlights falls on this corner and comes back to the motorist. So he's able to see that this is the edge of the road and avoid it. Now, this is taken from the internet, as we so often do nowadays. So it's always nice if you put a photograph on the internet, you would like other people to at least tell the world that you did this. So in this case, it's published by El Borgo, and there's something called a GNU free documentation license. He allows you to use it, but acknowledge the source. And of course, if someone takes it from you, they also should acknowledge the original source. So please do this when you use material from the internet. Now, we move to what happens to light when it travels from air to water. It bends, we call it refraction. Now here, what you have is an arrow showing a straight path of light, starting from A and reaching a point C on the surface. And then it bends and goes to a point B. So I've just drawn these two arrows of equal length. And the idea is that you take a point below A on the surface, take another point B above B on the surface. These two arrows are of equal length, but because of the change in direction, these two distances, small a to small c to small b, are not equal. In fact, that's a nice geometric way of stating the law of refraction, which you learn in school. Namely, in the case of light entering water, that this smaller distance, BC, will be 3/4 of this bigger distance, CA. Okay? And that continues to be true, even if we keep changing this angle. And this is called Snell's law. But like many things in science, it's not really named after the person who did it first. Okay. So again, acknowledging the source, which is this famous thing called Wikipedia. There's an article on the history of the laws of light. And looking at this figure, even if you did not know Arabic, you would guess that this person has figured out the law which governs, right? You have the same two line segments with a fixed ratio. And in this part of the figure, he's even designing a lens. So who is this person and when did he live? Well, his name is Ibn Sal. He lived in Cairo and more than 100 years ago, more than 1,000 years ago. So instead of talking of Snell's law, we should talk of it as Sal's law, except that Sal is really the name of his father. Right? Ibn Sal simply means the son of Sal. Okay. Now let's think a little more about the situation where light travels from air to water. What would a fish see? Let's ask this question. So I've shown you the same thing as on the previous slide. Number one happens to be a ray of light which gets bent, and this is how it travels. Now, if you were a fish living here and you looked in this direction, you would not see whatever was above the water at this point, because the light would bend, right, coming from here, and you will actually see what lies here. Okay? So the fish sees things at a different angle from what they would look from the surface. Okay? So let me draw a few more rays. So here is a ray number 2, which gets bent again. And now the third ray, I want to make it almost parallel to the surface of the water. Okay, I can't make it exactly parallel because then it wouldn't enter the water. Right? So here is ray number 3. So please imagine that this angle is very, very small. And then it comes out. And because of the law which we just stated, this distance is going to be shorter. So this angle is not very small, even though this angle is small. In fact, for light entering water, this angle is 48 degrees. Okay, so this is 42 degrees. So a fish looking up at an angle of 48 degrees to the vertical will actually see the entire sky. Okay. So what then happens if the fish decides to look at an angle greater than 48 degrees? Okay. So that's ray number 4, and you can now see that the angle with the vertical is greater than 48 degrees, greater than for ray C3, and therefore, what can it do? It cannot come out, so it gets reflected. So this is something we call total reflection. You don't need a laboratory to see this. If you have a fish tank at home, just lower your eye below the level of the fish tank and look upwards, just like the fish. Or even if you have a glass of water, fill it and look into the glass of water from below, and you will see it acting like a mirror. So this is called total reflection. So here is a nice picture illustrating total reflection. It's not taken by a fish. It's taken by a diver who works for the US Navy. Here is his name. He's looking up, and this is his companion who is on the top. This is some material floating on water, a cable. After all, this diver needs oxygen and so on, right? But the really interesting thing is that the whole sky now occupies this angle, which is called the Snell's window, which is an angle of 48 degrees. And all this is dark because, of course, it's a reflection, but then you go and look at the bottom, which is very dark. Okay. So we've learned different laws governing the behavior of light. Now, here is a picture of a famous mathematician, Pierre Fermat, who lived in the 17th century in France. And he is well known for something in mathematics. He proposed a problem which took 400 years to solve. Okay? He tried to solve it himself, but he could not. And basically he knew, and everyone knew, and all of you know, that 9 plus 16 is 25, or the square of 3 and the square of 4 add up to the square of 5. And he asked himself, can this be true? Even if you don't take square root, say you take the cube of 3, 27, and maybe the cube of some other number, will you get the cube of a third number? He thought about it, he tried various things and decided that's impossible. Except, of course, when the power is 2, right? So this is what we remember Fermat for. in mathematics and many other nice things he did. But what we should really be remembering him for today in the context of light is this. Okay. He gave a single law, and that's why I have called it a Fermat, which light has to obey in all the situations we've discussed so far. Okay. That light will travel along a path which takes the least possible time to go from the starting point to the end point. Okay. So let me illustrate this with a couple of stories. So the story begins near the seashore. So blue is the sea, and this is the beach. Okay. And here is a small boy, and he's obviously in a hurry. He seems to be running. And why is he running? Because there's a coconut tree here, and he's interested in eating some coconuts. And he wants to get there in the shortest possible time. Okay? And he can run at some speed on land, on the beach. So clearly, what he should be doing is taking the shortest path. Okay? And that's what he does. He goes there and enjoys his coconut. Okay? Now here is another boy, and you can see he's carrying a bucket because he's being given the duty of going and taking some water, okay, and pouring it on the coconut tree. Okay. So he can't just go straight to the coconut tree. He has to go to the water and then from there go to the coconut tree. So he has to do something like this. Now reaching the water clearly in the least possible time means he should go in a straight line. And from the water to the tree, he should again go in a straight line. But now he has a choice, which point to visit. He could do this, or he could, if he wants, he can go somewhere there and come back, but that will be very silly, it'll be much longer. So which point will make the sum of these two distances the shortest, and therefore enable him to reach in the least time? And if you work it out, Fermat worked it out. In fact, before him, in ancient Greece, a mathematician called Heron had worked it out, that these two angles will turn out to be equal, which is exactly what happens to a ray of light bouncing off a mirror. So the law of travel in a straight line, the law of reflection, are all contained in this idea of least time. But it gets better. So let's go to the next part of the story. So here is a person who is obviously very well built, very athletic. He's standing here, and you notice that he's wearing just a swimsuit. And the reason is that he's been employed to stand there and watch in the water. And if someone tries to go for a swim and they get into trouble, he can run very fast. Like Usain Bolt, he can run 100 meters in 10 seconds. And then once he gets into the water, like Michael Phelps, he can swim 100 meters in 50 seconds. Because, of course, swimming in water is much slower than running on land. And his job is to rescue anyone who's in trouble. And sure, sooner or later, some beginner goes and tries to swim and is not able to swim and cries out for help. So what does this person do? Well, maybe if it was some kind of film, he would run by the shortest possible path and rescue this person. But the shortest path in this case is not the path of least time. And the reason is there's a reasonably short journey in land and a longer journey in water where he's rather slow. So actually, if he was a mathematician, what he would do is take a longer journey on land, which he can cover very quickly, get close to the swimmer, and then go and rescue the swimmer, right? And again, you can ask, which point on the shore should he visit to reach the swimmer in the least possible time? And the answer is given by the same geometric law which we stated. So if you take this horizontal distance, it should be 5 times this short horizontal distance, because 5 is the ratio of the speed on land to the speed in water. So this is interesting. Fermat was really saying that because of this ratio of 4:3, the speed of light in water is less than in air. And at that time, no one had measured these speeds. So some people doubted it. In fact, at the same time, in Paris, there was another French scientist called Descartes, and he believed in the opposite. He thought the speed of light in glass or water would be faster than in air. Okay, so who was right? It had to be settled by experiment, but it took nearly 200 years to do the experiment. And when it was finally done, Fermat was proved right. Light does indeed travel more slowly in water or in glass than in air, and therefore his principle of least time proved to be a correct principle. Okay. But actually, there is a little more to the story. Okay. So right now, this person has been rescued, and the lifeguard has gone back to his station, and he now sees there are no swimmers. So he decides that he can now cool himself by swimming. He's an expert swimmer, as you can see, right? So no problem. But just as he gets into the water to enjoy his swim, one more person enters the water and cries out for help. So now what? He could again, let's say this distance is around 100 meters. He could just swim straight, and that would take him 50 seconds. But again, that's not the path of least time. What he should really be doing is getting to the shore, running on the shore, and that will happen just in 10 seconds, and then rescuing this person. So again, one can ask, what is this angle? And that angle is given by the same law that we discussed for light. So even the phenomenon of total reflection can be understood from the principle which was given by Fermat, the principle of least time. Okay, and this kind of propagation actually occurs. If you had two submarines and one of them sent out radio waves, some radio waves would reach directly, but some of them would actually go to the surface, travel along the surface, and go to the other submarine. Okay, so that's the power of the mathematical idea. Now, one of the reasons why people were unhappy with Fermat's principle of least time was it seems to attribute some kind of intelligence to light. Okay, it's how does it find the path of least time, right? And the answer was given again in the 17th century. Okay, and the answer is waves. Okay, so let me illustrate to you how, by using the idea of waves spreading out from a point, we can understand how light reaches its destination in the least possible time. Okay. So here is a source of waves, but again, to make it a story, let's imagine that this is a king, okay, who has huge armies at his disposal. Okay, any number of people who will obey whatever he says, and they have generals in the army, and they can also order people to do whatever they like. And they are supposed to find a treasure somewhere, but they don't know where the treasure is. So they send out a very large number of people. And you want to get to the treasure in the least possible time. So how do you do that? Okay. So the king first sends out his armies in all directions. And now they have reached this region. And of course, they have not found the treasure yet. So we are going to call this surface a front. Okay. And that's what military people call it. That's the front where the soldiers have reached. Now, what do these soldiers do from here? Well, they don't know where the treasure is. So from each point, they again spread out in all directions. Okay. All right. So that's from that point. And here are soldiers spreading out from this army. And here is another bunch of soldiers spreading. So You will now notice this front has advanced to a new position. And of course, I've only drawn 3 of these, but you should imagine such circles drawn around every point here. Okay. And then the front will be a curve which touches all these circles. So that's really a bigger circle in this case. And what do I mean by touching? Of course, I've drawn it a little separate. But once I bring it closer, each one of these circles will touch the bigger circle. But then we learned something interesting, that a lot of these soldiers are wasting their time because they're behind the front. The really useful people are the people like this person who have already reached the front. Okay. So now the soldiers realize that the best thing to do to advance to the next front is don't go in all directions. Go perpendicular to the front. Okay. Because that is the shortest path. Okay. So this is how this front advances, and sooner or later the front reaches the treasure and that particular soldier finds the treasure. Okay. So this is how waves reach their destination in a path of least time. Okay. So let me state this geometric construction again. Draw a circle from the starting point. Draw new circles from points on this front. Draw a curve touching all these circles. And let this curve travel perpendicular to itself. So you just draw lines perpendicular to this. And the length of each line depends on the speed at which light is traveling. It's such a beautiful idea. And it therefore tells you that light does not need any intelligence to reach its destination in the path of least time. It has to spread out in the form of waves. Now, the pioneer, as far as the wave theory of light is concerned, is this person who lived again in the 17th century in Holland. His name is, Huygens, and this geometric construction is called the Huygens construction. Okay. Now, this is a good concluding remark for this lecture, because Raman himself was fascinated by Huygens construction, which he must have learned when he was very young, and he has made beautiful use of it in many of his papers. Okay. So I hope that I've told you that some of the familiar things about light actually become more interesting if you go a little deeper. And of course, you can go much deeper by reading more about it. And I'll be happy to answer questions.